So this chapter, in chapter 6, we're going to talk about what it means to estimate using statistics, specifically to estimate parameters. So this brings together a bunch of different concepts from that we've been learning about. It brings together the normal distribution, it brings together probability in general, it brings together descriptive statistics. All these things are kind of brought together to talk about basically statistical inference. And if you study statistics more in depth, there's so much more I can talk about statistical inference. But being only a semester course, the main type of statistical inference that I want to talk about is a confidence interval. And a confidence interval is an interval of values that is used to estimate a population parameter. So let's review a little bit of terminology. All the way back to chapter 1, pretty much the first thing that we talked about was parameters versus statistics. And you probably know by now, or hopefully you know, that the population mean, which is a parameter, is mu, and the statistic is from a sample, and that's x bar. You could also talk about parameters for different things. For example, like sigma is a parameter, s is a statistic. This is standard deviation, right? Sigma squared is a parameter, that's variance. S squared is also variance, but it's a statistic. It's a sample variance, right? One thing that we haven't talked about as much, and we'll talk about it more in the last section of chapter 6, is p. Just a lowercase p is a proportion. If you have qualitative data, you may want to know the proportion of people that have blue eyes, for example. That is a parameter if you have a population, and it's p hat, and yes, it's literally a p with a little hat on it. If you want to know the proportion in a sample, that's a statistic. So all of these on the top are parameters, all these on the bottom are statistics. And what we're going to do is we're going to use statistics to make inferences and try to predict what the parameter is. Now what we're going to focus on is primarily, especially for the first two sections, is using x bar to try to predict what mu is. And then in the next section, or actually the last section, 6.3, we'll talk about how to use p hat to try to predict p. You can predict standard deviation. It's just a little bit more involved process that we just don't have time for at the moment. So basically, we are going to use sample statistics to estimate population parameters. And when you do this, you have something called a point estimate. A point estimate. And a point estimate is just a single value. It's just a single value for a population parameter. And the most unbiased point estimate for the population mean mu is x bar. So, for example, if you want to know what the population mean is, I can't possibly get the height of everybody in the world. But what I can do is get a sample of random people in the world, get that mean, which would be x bar, and use that x bar, which is my point estimate, to try to predict what mu is. Now the thing is whenever you estimate something, the first question you probably want to know is how accurate are you, right? I mean, if I want to estimate, if I had to take a guess of how of a measurement of something, I want to know, well, how accurate is that measurement? What's my error basically? And because a point estimate in and of itself does not have an error, it's just a single value. Well, that doesn't give us a lot of information. If I just have a point estimate and there's no error measurement to go along with it, that point estimate is kind of useless, because maybe my estimating skills are just really bad, and if they're really bad, I could be really far off from the actual value. So instead of just coming up with a point estimate, we start with a point estimate, but what we want to get to is an interval estimate. And an interval estimate is better because it's an actual range of values. It's an interval or range of values used to estimate a population parameter. So for example, like if this is a number line here, And let's say I get a sample, and I don't know what the sample is of, but let's say my mean of this sample is 20. So that's x bar. Okay. What I'm going to do is I'm also going to calculate a margin of error. Let's say my margin of error is, I don't know, 10. Oh, I just realized I skipped. $25, $30, $35, $40, $45. Okay, so if my margin of error is 10, that means that my mu is between 10 and 30. So having a margin of error of 10 in this example from 20 means that my mu is between 10 and 30. Because if I subtract 10, I'm at 10. If I add 10 to 20, I'm at 30, right? So what we're going to actually get is a range of values, like between 10 and 30, that actually gets us the interval estimate that we're talking about. And this interval is determined by something we call a level of confidence, which is denoted by a C, and we'll talk more about that in a little bit. But given this level of confidence, we calculate what's called a margin of error, capital E. And that's the greatest possible distance between the point estimate and the value of the parameter it is estimating. And capital E is Z sub C times sigma sub x bar. And you might say, well, what's this little sub C here? Well, we'll get to that. But first, remember that the Z score for that level of confidence is multiplied by sigma sub x bar. And sigma sub x bar is sigma over the square root of n. So this is what we talked about in the last section of chapter 5. Okay. Now there's a few stipulations here, because in order to use this technique, it is assumed you know the population standard deviation. So it is assumed you know sigma. And actually in real life, we don't really know sigma. Like, why would we know? Remember that sigma is the population standard deviation. Why would we be trying to estimate the population mean if we don't know the population standard deviation? And the truth is, we probably don't. But we'll find a way to remedy this later. We'll find a way so that we don't need the population standard deviation. But for now, we're just going to consider the fact that we know the population standard deviation. Okay? And so finally, a confidence interval for the population mean mu is x bar minus e, and we're going to use interval notation. So I'm going to put a parenthesis here, comma, x bar plus e. So this is not an ordered pair. This is just interval notation. So we start here to here. And the probability that the confidence interval contains mu is C. So C, before you create a confidence interval, so it's a probability before you create the confidence interval. That mu is in this interval. Okay, so you can actually control how wide or how close together the interval is depending on your level of confidence. All right, so this is a lot of background information. So let's do an actual example to show you what I'm talking about. So we have market researchers. And market researchers use the number of sentences per advertisement as a measure of readability for magazine advertisements. The following represents a random sample of the number of sentences found in 50 advertisements. Now, for every confidence interval, I'm going to write this at the top. Every confidence interval has 3 steps, at least for our purposes. 1, point estimate. In other words, what is the single value you are using to estimate the population parameter. 2, margin of error. And depending on what you know, that formula might look different, but so far our margin of error is z sub c times sigma over the square root of n. And then 3, we take our point estimate, which is x bar in this case. We take our point estimate and we add and subtract our margin of error. But this is the same thing every time, right? We have our point estimate, we have our margin of error, we add and subtract the margin of error from our point estimate. Okay, so the first thing we're going to do in step 1, or part A of this problem, is find the point estimate. Well, the point estimate is x bar. What is the average number of sentences in the magazine advertisement? So we have to average all these numbers. Well, to average something, you should know you need to add everything together and divide by how many there are. And I'll just tell you, if you add all these together, you get 620, and there's 50. So that's 12.4. Okay? So that's the first step, easy enough. The hardest step is probably finding the margin of error. So we want to find the margin of error for the mean number of sentences in all magazine advertisements for a 95% confidence level. Assume the population standard deviation is about 5.0. So my margin of error formula is z sub c times sigma over the square root of n. Z sub c is determined by a normal distribution because if you read the problem, we have 50 magazine advertisements. And we know that the sampling distribution of sample means is approximately normal if our sample size is greater than 30. Our central limit theorem kicks in here. And because our central limit theorem kicks in, we can draw a normal distribution. And when it says 95% confidence, that means we want the 95% that is in the middle. So we have to do a little bit of thinking here. Well, if we have 95% in the middle, if it's 95% confidence, then that means this blue area is 2.5% or 0.0250. So we need to find our z sub c is going to be for 95% confidence. And we need to find in our chart, we need to look up 0.0250 because that's the area to the left. So the normal distribution chart is not going away. We need to look that up. Okay, so let me get my I believe I saved it in here. Here we go. All right, 0.0250, and that one is exactly, move this so you can zoom in a little bit. That one is exactly in there. So that's the area, remember. So we want to find the z-score for that, and that is negative 1.96. So that's our z-score. Negative 1.96. Now, because it's actually two z-scores, 1.96 and negative 1.96, because it's symmetric and you're adding and subtracting the margin of error. So even though it's negative 1.96 when I look it up, I'm actually going to use in my calculation 1.96, and then that way I can just add and subtract 1.96 later. Okay, times the sigma over the square root of n. Now sigma is easy. They tell you what the population standard deviation is. That's 5.0. And n is also easy. We already used that. It's 50 because there's 50 magazine advertisements. And when you do this calculation, if you multiply it all out using your calculator, you get 1.4. And I'm rounding only again to one decimal place because I have whole numbers in my data set, so only one decimal place is as accurate as I need to be. So that's the margin of error part. So when I take the margin of error, I get 1.4, and then the third step is, I'll go back up here, to add and subtract the margin of error from my point estimate. So my point estimate is 12.4. My margin of error is 1.4, so I'm going to add and subtract 1.4 from 12.4. So x bar plus or minus e is 12.4 plus or minus 1.4. So when I subtract, you always do the smaller number first. I get 11.0, and when I add, I get 13.8. And we do need to write this in a complete sentence to interpret it. So what is this interval? Well, it means, because we had a 95% confidence level, and we always start with that. So with 95% confidence, the population mean number of sentences in magazine advertisements is between 11.0 and 13.8. So once again, this is a 95% confidence. So if I were to do this 95 times, if I were to do this 100 times, let's say, 95 of the samples, and when I say do this 100 times, I mean get 100 different samples. 95 of the samples would contain the population parameter. Because we're at 95% confidence, the parameter may not be between these two numbers. It may be outside these two numbers. Okay? Okay, let's do the same thing, but let's construct a 99% confidence interval for the mean number of sentences in all magazine advertisements. So everything is the same. We're starting from the very beginning, except all we're doing is changing 95 to 99%. So the first step is still the same, x bar. That's still calculated to be 12.4. The margin of error is going to be different though, because now we're at 99%. So think of what changes in this formula. I would pause the video here, think of what changes, see if you can find the correct margin of error for 99%. So hopefully you tried to attempt this on your own, and if you did that, you would get, when you draw your bell curve, instead of 95% in the middle, you're going to put 99%. And I put a lot of space on each side of this, but that's okay, because there was only 1%. So this is 0.0050, because remember, this is only 0.5%, right? Because I have 0.5% on this side and 0.5% on this side. So I want to find the z-score for 0.0500, or excuse me, 0.005. And to do that, we can look at our handy dandy charts. 0.005. And it looks like, once again, excuse me, looks like we have two. We have 0.0051 and 0.0049. So 0.0051 is negative 2.57, and 0.0049 is negative 2.58. So what's exactly in between negative 2.57 and negative 2.58? Well, that's negative 2.575, because these are the same distance away, right? These are the same distance away from 0.005. So I have to average negative 2.57 and negative 2.58. And that's negative 2.575. But I'm going to use the positive z-score in my actual calculation. So I'm going to have 2.575. We have 5.0 divided by the square root of 50. That's 1.8. Then we add and subtract that margin of error from x bar. That becomes 10.6 to 14.2. So we say with 99% confidence, population mean Number of sentences in magazine. Advertisements is between 10.6 and 14.2. All right. Now notice the difference here. Before we move on, I want you to notice and compare these. So the first one is between 11.0 and 13.8. The next one is between 10.6 and 14.2. So what happened? And if you look closely, you'll see, if you compare the intervals here, if I compare this one to this one, that the width increased, right? We went from 10.6 to 14.2, and that's because our confidence level went up. And I always like to give the analogy of SpongeBob and Jellyfish Fields. So if SpongeBob in Jellyfish Fields wants to catch jellyfish, he's probably more confident he'll catch jellyfish if he has a bigger net, right? So the bigger the net, the more area he has. If it's a really small net, it's harder to catch the jellyfish because there's not as much area in the net to catch them. So that's the same thing. To capture our population parameter, we're more confident we're going to capture our population parameter if we have a bigger net. So our confidence level goes up. But at what cost? Well, the cost is that we have more error, right? If we compare our errors, this one I'm adding and subtracting 1.4, and this one I'm adding and subtracting 1.8. So I have a little bit more error, actually a good amount more error, to go from 95% to 99% confidence. So it's kind of a balancing act. Are you willing to be more confident and have more error for that confidence in your final result? All right. So try to do the next one on your own because this is a totally different problem, but it's still the same concepts that you're applying. So try to do the 3 steps to calculate the confidence interval and see what you come up with. Okay, so hopefully pause the video to attempt this on your own. So it says a college admission director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. The mean age is found to be 22.9 years. From past studies, the standard deviation is known to be 1.5 years. The population is normally distributed. Construct a 90% confidence interval of the population mean age. All right, so first things first. First step is X bar. Now in the previous section I gave you a data set. In the previous problem I gave you a data set and we actually had to average them. But we don't have to average anything here. They tell us the mean age is found to be 22.9, and usually they'll give it to us. We don't actually have to average anything ourselves. All right, 2, the margin of error. Z-score times sigma over the square root of n. Well, hardest part's the z-score, so let's get this out of the way. So we're going to draw a normal curve, approximately normal curve. We have 90% in the middle, so if there's 90% in the middle, how much is on either side? It's 5%, right? Which is 0.0500. Now this is different than 0.5%, right? So don't let that confuse you. So you have to be careful about watching your zeros. So 0.05 is... Well, here's 0.0505 and here's 0.0495. So which one's closer? It looks like they're the same distance away, and if you remember, that's the 5th percentile. The 5th percentile z-score is negative 1.645 because this is negative 1.64. Oops, try to get these both in here. Yep, negative 1.64, negative 1.65. So it's right in between the two. So it's negative 1.645 and 1.645. And as I always say, I use the positive. Standard deviation is 1.5. Sample size is 20. Don't forget to take the square root. And you end up with a margin of error of 0.6. Then we add and subtract the margin of error from our point estimate. So it's 22.3, and when we add this, 23.5. So with 90% confidence, the population mean age of, and notice how I say population mean age, right? This is an inference about the population. I'm using the sample to make an inference about population. You do not say the word sample in the sentence. You do not say the word, I didn't say anything about the 20 that I gathered. I'm just giving the result, right? The sentence is all about the result and how to interpret the result. It has nothing to do with the sample itself. It's about making an inference about the population. So the population of mean age of students at a college is between 22.3 and 23.5 years. It's probably understood to be years, but that's okay. All right. So that's creating confidence intervals if you know the population standard deviation. Okay. So now what we're going to talk about, the last concept here, is actually doing this in reverse. So sometimes you may encounter, or statisticians really encounter this a lot, is they'll go up to a scientist and they'll say, okay, or a scientist will actually come up to them and they'll say, okay, the scientist says, I want to do this experiment, but I want to know how much data do I need to be accurate within a certain amount. And the statistician will do some calculations and try to determine that. But basically they'll say, okay, I want my confidence level to be something, and I know my population standard deviation is around this, and I want my margin of error to be this. So basically we're going to solve for n. What is n? How much data do I need to be accurate? So what we can do is we can take this formula and we can multiply both sides by the square root of n. So we have the square root of n times e equals e sub c sigma. And we can divide both sides by e. And we can square both sides. And basically, we can solve for n. So n, after we square both sides, is z sub c sigma over e quantity squared. So if we know our confidence level, our population standard deviation, and our margin of error, we can estimate what n is, what our sample size we need is. So let's do an example using this. Oh, and I almost forgot, if sigma is unknown, you can use s if you have at least 30 members. And remember, sigma is the population standard deviation, and s is the sample standard deviation, because many times we don't know what S sigma is, but we do know S. Okay, so it says you want to estimate the mean number of sentences in a magazine advertisement. Assume the population standard deviation is 5.0. How many magazine advertisements must be included in the sample if you want to be 95% confident the sample mean is within one sentence of the population mean? So first of all, my question is, how many magazine advertisements must be included? So basically it's asking for a sample size. All right, so z sub c, well, it's 95% confidence, and you should go back. What is the z-score for 95% confidence? And that is 1.96. And actually, 95% confidence comes up so much. This is just one worth remembering. If you remember that the z-score for 95% confidence is 1.96, you're doing yourself a favor. Okay, sigma is 5.0. And then what's our margin of error? Well, It says within one sentence, right? I want my error to be within 1, so I'm just dividing by 1. Quantity squared. And when you do this calculation, you get 96.04. But you probably know, and if you're thinking about this, you may realize, well, can you sample 96.04 magazine advertisements? And the answer is no, right? You either sample it or you don't. So you always round up for sample size. So my answer is actually slightly dyslexic there. 97. So you always round up, because if I go anything below 96.04, then it's not going to be accurate enough. It's like the problems in elementary school, right? Where you calculate you need 5.2 gallons of paint. Does that mean you're going to buy 5 gallons of paint? No, you're going to buy 6, so you can paint the room. Okay, so why don't you try to do this next one on your own? It's using the same formula, and see if you can come up with the margin of error. Alright, so this one is about a beverage company, and it uses a machine to fill 1 liter bottles with water. Assume that the population of volumes is normally distributed. The company wants to estimate the mean volume of water the machine is putting in the bottles within 1 millimeter. Determine the minimum sample size required to construct a 95% confidence interval for the population mean. Assume the population standard deviation is 3 millimeters. So again, hopefully you figured this out on your own. But my my z-score is 1.96 because it's 95%. My sigma, it says, is 5.0. Or no, not 5.0. It's 3. Standard deviation is 3. Sorry. And then the we want to be within 1 millimeter again. So my sample size should be about 35. That's after rounding up. Let's do the same thing for the bottom, but this time we want an error tolerance of 2. So everything is the same in the formula. It's still 1.96 times 3, but now we're dividing by 2. Again, don't forget to square it. A lot of people forget to square it. And we get 9. So if we wanted more error, if we accept more error, so this error tolerance is 2, whereas the previous is 1, what happens? Well, we don't need as much of a sample size, right? So a smaller margin of error requires a larger sample size, right? If you want smaller error, you need a larger sample size, which makes sense. You know, it takes more work to be more accurate, right? So a smaller margin of error requires a larger sample size, and then the reverse is also true. A larger margin of error requires a smaller sample size. All right, so try to do the Math Excel homework, and let me know if you have any questions.